thì bắt tỉnh nơi. À, rồi bạn cuối xem. Không biết là thầy sẽ dạy cái gì hôm nay mà thầy
ủng hộ được. Bắt đầu học ạ. Chúng ta bắt đầu học. Hôm nay bắt đầu bằng 2 câu tiếng Việt. Vừa nãy trước khi trong lúc tôi đang chuẩn bị cái laptop thì có một bạn lên nói thầy ơi sắp thi giữa kỳ rồi mà trong đầu em ít chữ quá khéo trượt. Cái đó thì chắc là thầy giáo cũng chẳng giúp gì được cả các bạn, thì học là việc của các bạn thôi, các bạn cứ lo đâu. Cái thứ hai có một bạn nào đó tôi không nhớ, các bạn có phàn nàn lên là trong giờ bài tập thầy giáo cô giáo không có giải thích kỹ lắm mà chỉ viết lời giải ra cho các bạn. Thì tôi luôn luôn nhắc rằng quyền lợi của các bạn là hỏi thầy giáo. Tôi rất thích giữa giờ các bạn lên đây hỏi, và cũng như vậy trong giờ bài tập các bạn có thể hỏi, đừng có chép. Cứ cô cho bài tập, thầy cho bài tập thì xong rồi thầy chữa chép, mà mình có quyền hỏi tại sao như này, tại sao như kia. Đấy là quyền lợi của các bạn. Thi giữa kỳ thì chúng ta sẽ thi đến hết cái bài giảng thứ 4 về không gian vector. Những điều mà chúng ta sắp sửa học buổi hôm nay thì sẽ được thi vào cuối kỳ. Đương nhiên thi cuối kỳ cũng vẫn thi lại tất cả những kiến thức mà chúng ta đã học từ đầu, bởi vì không có cái đấy thì không làm được cái bài cuối cùng đâu. So I make a short review of point we studied last week. Last week we made a very short contents of the course. So last week we begin with the space, the null space of A. The null space of A denoted by NSA. That is a space of solution of homogeneous system of linear equation Ax equals 0. And here means that we are given n by n, which is A. And we have an observation saying that the row space of A and the column space of A, they have the same dimension, and that dimension is defined to be the rank of A, or by formula you have it here. And one of your exercise, that is how to find the rank of A, and it is explained already. I will not explain in detail here. And more than that, we have the notion of nullity. The nullity of a matrix A, that is the dimension of the null space of A, or the dimension of the solution space of Ax equals 0. And by formula you have that one. And you see, the rank and the nullity will have a relation to each other. And they are related to each other by the formula like that. If the matrix A has n columns, the number of columns of A is n, then the sum of rank A and nullity of A equals exactly n. So if we know the rank of A, then we know immediately the nullity, and vice versa. If you are given the nullity of A, then you find easily the rank of A. And the meaning of the rank and the meaning of nullity is following. You know that from the beginning of the course, we pay our attention to solving a system of linear equation. And the first one, that is, we consider the homogeneous system of linear equation Ax equals 0. So in solving the system of linear equation, we need to know how many free variables and how many leading variables we have. And the number of free variables is exactly the nullity of A, and the number of leading variables is rank of A. So that will give you the meaning of rank and the nullity of any matrix A. And after that, and after everything, then we try to solve any system of linear equation. Now, by any system of linear equation, I mean the right-hand side is not 0. It can be any right-hand side. Or by Ax equals B, I mean the right-hand side B can be anything. And obviously, whenever you are given a system like that, you can consider the homogeneous system of linear equation Ax equals 0, like that one. Then, if for Ax equals 0, we know already how to find any solution, and we denoted any solution by SH. Then, if you can find a particular solution for Ax equals B, denoted by XB, then any other solution of Ax could be must be of the form XB plus SH here. Then that gives you a way to solve any non-homogeneous system of linear equation. And before solving a system of linear equation, first you need to know if the system has solution or not, or you need to decide that Ax equals B is consistent or not. Then here give you a criterion to verify the system Ax equals B is consistent if and only if B is lying in the column space of A. And column space of A, we know already how to find it. How to find it, you know. And from here, you have one more criterion to verify. That criterion is very easy to verify. It says that if you have the rank of the augmented matrix A, B equal the rank of coefficient matrix, then the system Ax could be must be consistent. Must be consistent. That is about the non-homogeneous system of linear equation. Then I turn into the case of square matrix, and I summarize some conditions for you. Let A to be a square matrix of order n. Then A is invertible if and only if Ax equals B has unique solution for any right-hand side column B, or it is equivalent to Ax 0 has only trivial solution. And the new one from last week is that A is invariable will be equivalent to the rank of the matrix A equal n. And that condition is again equivalent to the fact that n row vectors of A are linearly independent, or the n columns vectors of A are linearly independent. And last week I forget one thing, and now I add it here. That is, A is invariable if and only if the determinant of A is non-zero. A has a non-zero determinant. Then we change to another problems of a vector space. That is about the basis and coordinate. And as I told you, one of most important property of a basis is the following. Suppose that B is a basis for vector space V. Then any vector x inside V can be written uniquely as a linear combination x equals C1 V1 plus C2 V2 plus Cn Vn. And because the way writing x like that is unique, we have only one way to write it, then the number C1, C2, Cn will be called the coordinate of x relative to the basis B. And we denote it by that. Usually we write it in the column like that one. So here is a coordinate column or coordinate basis of x. And because it depends on the basis B, so I need to write the subscript B here. It says that the coordinate is relative to the basis B. But we know already that a vector space usually will have many bases. Then suppose that we know the coordinate of a vector relative to one basis B, and you are asked to find the coordinate of the same vector but now relative to another basis B prime. How to do it? And here is some explanation for you. Suppose that B equal U1 up to UN and B prime from U1 prime up to UN prime. Suppose that there are two bases for the same vector space V. And now I denoted V sub B is a coordinate matrix of V relative to B, and V sub B prime is a coordinate matrix of V relative to B prime. Then those coordinate matrices, coordinate columns will be related to each other by the formula, by that formula. And V, we can say VB equal P multiplied by VB prime. So what is the P? The P is a matrix consisting of n columns like that one. I will not explain to you what is here because it is explained in the previous slide. The matrix P has named transition matrix from B prime to B. We change from the coordinate in B prime into coordinate in relative to B. And because the role of B and B prime are the same, B và B phẩy có cùng vai trò như nhau. Then if we can change the coordinate from B prime to B, we can do the same thing. We can change the coordinate from B back to B prime. So that is P. If P is a transition basis from B prime to basis B in Rn, then P must be invertible. And then this transition matrix now from B to B prime will be P inverse, or If you want to write it in the formula, you have that one. B like that, B prime like that. Then V, the coordinate of V related to B equal P multiplied to the coordinate of V related to B prime, where P to be that matrix and the coordinate of V related to B prime equals that matrix multiplied to the coordinate of V related to B, and that matrix is exactly the inverse of P. It's here. And then again, you need to find the transition matrix, because in here you see the most important point, the key point you need to do, that is to find transition matrix. How to do it? How to find it? Suppose that you are given two matrices, B and B prime. How to find the transition matrix from B prime to B or from B to B prime? It is here. We can do it by using Gauss-Jordan eliminations. And we write, if you want to find the transition matrix from B to B prime, you need to write B prime first and then B. And then we apply Gauss-Jordan elimination on the first part. When the first part became here, the second part will be the transition matrix from B to B prime. And as I told you in the previous slide, it is a P inverse. So that is on what we studied last week. And today we will begin a new lecture. The new lecture is about space with inner product inside it. And I want to tell you once again, it will coming back to high school. The inner product space, inner product here in high school you study already. In high school you call it tích vô hướng. So whenever you find something difficult, try to think of tích vô hướng in high school and everything will be as you know already. First, now we consider the space Rn, that is n space. That is quite familiar to us, and in case you need to have some geometry, some imagination, please take n equal 2 or 3, and everything will be in front of you very easy. Now, suppose that we consider a vector, say V inside Rn. Then we can define the length of the vector V. The length of the vector V is given by that square root of V1 squared plus V2 squared plus Vn squared. And you can try n equal 2. It's very easy. That is what you did already many times in high school, I promise. And then the length of a vector, sometimes we call it norm. The norm of a vector in Vietnamese, the norm, chuẩn của một vector, the norm of a vector. So the following property of length is very familiar to you. The length must be non-negative. Tôi nghĩ là giày dép thì các thứ nó đều co lại, kể cả tiếng các bạn đang tám ở trong lớp nó cũng phải bé lại mà nó vẫn to như thường. So here are some property of length. The first one is that the length must be non-negative, and the second one is not property. Second one just only the name. If a vector has a length 1, we call it unit vector. Vector mà có độ dài bằng 1 thường được gọi là vector đơn vị. The length equal 0 if and only if v is a zero vector. And the last one, if we take any number c multiplied by v, then the length of that equals absolute value of c multiplied by the length of v. So everything is very easy for you to see, to imagine, and to verify. You can verify it by the formula here. And the next slide will show you here. Suppose that we are given the vector v like that with the coordinate like that one. Then the length equals that, and that by calculation I get the length is 1. So v now is unit vector. We consider another example that is in R5. We are given a vector v with the coordinate like that, then the length of v equals 5. So at least up to this slide everything is very easy. The next one, in Rn, we know already that we have a standard basis by E1, E2, En. And it is very easy for you to verify that on the vector in the standard basis will be unit vector on of them has a length 1. Has length 1. For example, if you consider R2, you have two standard unit or standard basis ij, I with the coordinate 1, 0, j is coordinate 0, 1. And standard unit vector inside R3. They are standard basis I, j, and k with coordinate like that, and you can verify that we have the length 1. Now, in case we have two vectors, both of them are non-zero vectors, and they are parallel to each other, then they are parallel if and only if they can be written like that: U equals C tie of V. Then, if the number C is a positive, C cannot be 0 because both of vector U and V are not zero vector. So if C is a positive, we say that U and V has the same direction. The same direction because they direct to one direction. If C is a negative, we say U and V have opposite direction. Because in that case, one vector show this way, and the other vector will show the other way. Now, I repeat for you the property number 4, saying that C, the length of C multiplied by V equals absolute value of C multiplied by V. So, just only to repeat it here, and I want to insist that because the length is non-negative, so you cannot multiply C here only. You need to get the absolute value of C multiplied by V. Okay. And the explanation is given here. And now that is something about the unit vector. Suppose that V is a non-zero vector. V is a non-zero vector inside I. Then if we take V and then we divide it by the length of V, or that is we multiply V by 1 over the length of V. Then we get a new vector denoted by U. And obviously the new vector U which has a length 1. Then we call it the unit vector in the same direction of V. Vector đơn vị cùng hướng với V. That is the name. And here is some very easy explanation for you. Here, once again, I call and I give you the name, the vector V divided by the length of V will be called the unit vector in the direction of V. And the procedure, the processing, when we turn from V into V over the length of V, has name normalizing process of the vector V. Quá trình chuẩn hóa một vector V. Tôi có một vector V, tôi khắc công, tôi chia cho độ dài của nó thì tôi sẽ được một vector cùng hướng với V và có độ dài bằng 1. Quá trình đấy gọi là chuẩn hóa một vector. Now, here is some examples. You are given a vector V. You need to find the unit vector in the same direction with V. Then, the first one, we need to find the length of V. By the formula, it is the square root of 14. Then, V over length of V to be that. So we get that vector and we can verify that vector which has a length 1. That is V over the length of V is unit vector and it is the same direction. It's the same direction with V. The next one, again, we know already in high school. Suppose that we are given two vectors U and V. Then we can define the distance between U and V. Khoảng cách giữa hai vector. The distance between U and V to be that you take the difference U minus V and then you take the length of that. It is defined to be the distance between two vectors U and V. And again, the following property of distance you know already. The distance between two vectors is non-negative. It's never be negative. Second one, d of U and V, the distance between U and V equals 0 if and only if U and V are the same. And the last one, the distance between U and V equals the distance between V and U. Khoảng cách giữa A và B với khoảng cách giữa B và A là như nhau, không có gì khác. Here are some examples about calculation. Suppose that you are given two vectors U and V in R3 like that. Then the distance between U and V to be that one. We just only using the formula in the previous slide, you get the distance between U and V to be that one. And now the dot product in Rn. In English, they call it the dot product, but I believe that in high school you call that one is tích vô hướng. Okay, suppose that you are given U and V. There are two vectors inside Rn. Then the dot product of U and V is the following one. U dot V V equal U1 V1 plus U2 V2 plus UN Vn. It has name dot product because the notation is a dot here. And please remember for me, dot product is a number. Dot product is a number. If you take vector U and vector V, you take the dot product of two vectors. What you get? You get a number. That is not a new vector, you get a number. Tích vô hướng của hai vector là một số. Đấy là điều. That is what you need to remember. Examples. If you are given U and V like that, then dot product will be minus 7. And dot product will have the following property. It has 4 properties. Or 5 properties. The first one saying U dot V equal V dot U. The second property here is distributivity. The third one to be that one. If you take C, any number C multiplied by the dot product of V, it equals that. You take C multiplied by one of vector and then take the product like that. And the fourth one saying dot product of V Bayesian equals square of the length. And the last one saying the dot product is of V and V is always non-negative and it equals 0 if and only if V is the zero vector. Tôi nhìn thấy bạn kia nói chuyện mấy lần rồi đấy ạ. Sao, có chuyện gì vui thế ạ? Hay là mời bạn lên đây nói chuyện với tôi ạ? Đừng để tôi nhắc một lần nữa và đừng để tôi chỉ người nào hoặc là tôi mời lên đây ngồi hoặc là tôi đề nghị mời em ra chỗ kia ngồi, mời em ra chỗ kia ngồi. Các bạn không phải trẻ con, tôi không thích làm việc đấy, nhớ chưa? Đừng để tôi nhắc. So we have a 5 property for the dot product here. Now I give you the name. Now the space Rn together with the dot product will have the name Euclidean n space. Không gian Euclid Rn. That is the vector space Rn together with the dot product we have just defined. So that is an Euclidean space. Không gian Euclid là cái chúng ta đã học ở phổ thông. Chỉ có điều ở phổ thông chúng ta chỉ học với không gian 2 chiều, không gian 3 chiều. But here you see, if we define it for any number n, nothing new. Nothing new. The next one, here. The examples for you to find the dot product. Suppose that you are given U, V, and W like that. That is, there are 3 vectors inside R2. That is 3 vectors on the coordinate plane. You are required to find U dot V, U dot V, and then dot W. And here you have 5 exercises. Then the first one, by formula you get, is minus 6. The next one, here, just only applying 5 property in the previous slide, you can find anything. And the last one, just a little more difficult, not more complicated, just a little longer for you to find. And here, just a little more just the same kind of exercise for you. So I will go very fast about that one. Now, that one is what I want to insist. That is Cauchy-Schwarz inequality. That is, if you are given two vectors u and v inside I, then you get that one. And here, by u dot v like that, we denote the absolute value of the dot product u and v. And I claim that is always true. And here you can verify. Suppose that you are given u like that one and v like that one, then u dot v will be -1, u dot u 11, and v dot v equal 5. Then on the right hand side, on the left hand side you get, on the left hand side is 1, on the right hand side you get square root of 55. Then obviously you get that one. But however, I want to tell you, the name is Cauchy inequality. But the Cauchy, it is quite familiar to you. Now please take a look here. Suppose that if you have u to be that one, v to be that one, there are two vectors inside R2. Then the inequality we have is here. Now I want to explain about that one. On the left hand side, u, the absolute value of u dot v to be absolute value of u1 v1 plus u2 v2. And on the right hand side, you get the product of two lengths here. The length of u is here, the length of v to be that one. Then, if we take square of left hand side, you will get that one. Square of that. And square of right hand side, you get square of that one. And if you compare the left hand side and right hand side here, you will get that one. And that one is exactly what we know from high school. That is Cauchy inequality. That one is Cauchy inequality. The next, so for the Euclidean space, we define the length, the norm, normalizing vector, and we define dot product. Now we define the angle between two vectors u and v. Suppose that we are given two vectors u and v inside I. Then the angle between the two vectors u and v will be the angles zeta, satisfying the following. The cosine of zeta equals u dot v over the product of lengths of u and the length of v. Here zeta is a value lying between 0 and pi. And I explain to you, we have five cases like here. The first one is here, second one is here, and the middle one is here, and fourth one and the fifth one is here. For the first one, the two vectors u and v are in opposite direction. And for the second one, we have the dot product of u and v is negative. And in the middle one, we have u and v are the dot product of u and v are 0. And here the dot product is positive, and in that case, two vectors u and v are the same direction. Or you can see, in the first case, the zeta equal pi. And here, for the second case, zeta lying between the pi over 2 and pi. And here is zeta is exactly 1/2 of pi. And here zeta is more than 0 and less than pi over 2. and the last one is 0 equal, zeta equals 0. And in 5 cases, you have the value of the cosine to be z1. And obviously, you see, because I put zeta equal pi over 2 in Sweden, that will be most important in this lecture, lecture number 5. That case must be most studied in this lecture. Okay. The first remark I would like to tell you. Here we define the angle between two vectors u and v, but always we require that both vectors u and v are non-zero. We cannot define the angle between zero vector and another vector. Không thể nào định nghĩa được góc giữa vector không và một vector bất kỳ khác, cái đấy không bao giờ định nghĩa. Here, suppose that you are required to find the angle between the two vectors like that in R4. Then, the length of u to be that, the length of v to be z1, and dot product to be z1. Then, the angle between the two to be that, to be zeta, satisfying the cosine of zeta to be z1. And because of that, we see in that case zeta must be pi, or u and v will have opposite direction. One vector showing this way and the other showing the other way. Or if you look at the coordinate, you will see u equal minus 2 times of v. U equal minus 2 times of v. Now I go into the case in the middle. That is the case when the angle zeta equal pi over 2. Two vectors u and v will be called orthogonal if their dot product equal 0. Hai vector được gọi là vuông góc nếu tích dot của chúng là bằng 0. That remark is somehow funny. In previous slide, I said to you that we cannot define the angle between the zero vector and another vector. But however, here we consider that the zero vector is orthogonal to any other vector. Người ta không thể định nghĩa được góc giữa vector không và một vector khác, nhưng người ta lại quy ước là vector không là vuông góc với mọi vector khác. Nhớ một cái điều đấy, đừng quên vector không là trực giao với mọi vector khác. Now examples. Please find all vectors in the plane which are orthogonal to u to be z1. So how to do it? U to be here, and suppose that v is any vector with the coordinate v1 and v2. And if v is orthogonal to u, it means that u dot v must be 0, and u dot v to be z1. So we need to find v1, v2 satisfying that equation. And that one is so funny because the system of linear equation consists only one linear equation. We solve it by applying Gauss elimination. We get the solution is here. V1 equal minus t over 2 and v2 is t. And here, any vector with a coordinate like that must be orthogonal to u. But what I want to ask you, in case now, you consider that one is very easy to see because it is a vectors on the plane. So so here is a vector u. So what is the vector v? Okay. Any vector v orthogonal to u must be lying on the any vector lying on that straight line will be orthogonal to u, or that one is equation for a straight line, or it is if you could want to say some things more than high school, you say that will give you a subspace of atom, then con của mặt phẳng. That is something can be considered just a little higher than high school. But however, it is a straight line. Nó là một đường thẳng vuông góc với vector đó, và cái đấy thì các bạn đã biết từ phổ thông rồi. Tôi có một cái thằng này, bất kỳ cái nào vuông góc thì nó đều nằm trên một cái đường thẳng. You can try similar examples for case A3. I will not do it here. Now is triangle inequality. Suppose that you are given two vectors u and v in Rn. Then you have that one. The length of u plus v less than or equal the length of u plus the length of v. And it has named the triangle inequality. Bất等thức tam giác. And that, once again, you know from the high school. Why that? Because in high school you know if you are given u like that, v like that, then the other side of the triangle, that will be u plus v. And the length of one side of triangle must be less than or equal the length of u and v. That we know already. So that is here. And the explanation is given in the slide on the Moodle. You can read it by yourself. What I want to tell you, that is, here we have less than or equal. So when you have the equality, khi nào thì có dấu bằng? We have equality if and only if u and v have the same direction. U and v has the same direction. Or here you can see. If and only if that point will down here, then the length of u will be here, the length of v will be here, and the length of u and v to be here. So anything we study here, it looks somehow very high, very academic, very horrible for you. But if you look it back by your knowledge in high school, by geometry, it is what you know already. The next one will be Pythagorean theorem, định lý Pythagore. The Pythagorean theorem saying U and V are orthogonal to each other if and only if we have that one. Square of the length of U plus V equals U square, the length U square plus the length of V square. Like that. I will not explain to you. You can verify it and please consider it in the case n equal 2, n equal 3. You get that? And you can verify it by the formula because we have it here. What I want to explain to you in the next slide is the following. Now so far we know the dot product. The dot product we know, and we know a vector. Usually we write it in the columns. The coordinate will be written in the column matrix. Then now we have another way to say about the dot product by using matrix multiplication. A vector U will be presented in the column like that. But if we take U as a rows matrix, not columns, like that, then we can multiply them together. And if we multiply them together, we get Z1. And Z1 is exactly the dot product of U and V. So we get that formula. The dot product of U and V equals U transpose multiplied by V. So that is what I want to insist here. In order to find the dot product of two vectors in Rn, you can apply the matrix multiplication like that one. In some of your exercise, you need to remember that one, that way of writing. So that is all about Euclidean space. And after the break, we begin the definition of inner product space. Sau giờ nghỉ chúng ta sẽ học cái không gian với lại cái tích vô hướng một cách tổng quát. Vừa rồi chúng ta mới học cái không gian Rn, cái không gian mà ở phổ thông thì chúng ta gọi là không gian Euclid. Nghỉ giải lao 5 phút. Chúng ta học tiếp ạ. So before the break, we study already the Euclidean space, but it is not the new one. That is not new one. Just only to revise what we study already in high school, but we make it just a little bigger, a little more general. That is, instead of consider the plane of space, now we consider n space An. Now we begin define that one, the notion of inner product space. That is no longer n space. That is any vector space. So suppose that V is a vector space, and suppose that inside V we are given a function like as follows. The function sending any pair of two vector uv to a real number, we denote it by uv inside the sharp bracket like that one. And that function satisfies following four axioms. The first one saying uv equal vu. The second one to be that. The third one to be that one. And the last one saying the value of the function on vv is non-negative and it equals 0 if and only if v is 0 vector. If we can find a function like that on v, then the function will be called the inner product on v. The function will be called the inner product on v. So now we define already the inner product. And the next one, I remind you in An we have the dot product denoted by u dot v. But now in vector space, whenever we define inner product, it will be denoted by u and v lying in between of the sharp bracket like that one. Ở không gian RN chúng ta định nghĩa cái tích vô hướng và ký hiệu nó bởi dấu chấm gọi là dot product. Ở đây chúng ta định nghĩa tích trong và chúng ta ký hiệu nó bằng u, v đặt trong hai cái dấu ngoặc nhọn như thế này, in the sharp product. Now a vector space V together with an inner product will be called an inner product space. Once again, the vector space consisting of V and two operations plus and fact dot like that. But now inner product space is a vector space together with an inner product inside here. The first example saying that the Euclidean space Rn together with dot product will be an inner product space. That is obvious because we know all property for dot product in Rn are the same, satisfying four property in definition of inner product. So it's here. Or you can verify. Suppose that u v to be that one, then the first property saying u v to be that one, and then that product will satisfy all four axioms here. The next one, now please pay attention to the formula. we are given here. Suppose that U to be Z1, V to be Z1, there are two vectors inside R2. Now we define a new function UV equal U1 V1 plus 2 times of U2 V2. That is not the dot product. That is a not usual dot product. That is something new because here you have the number 2 here. And we need to verify if the new function satisfies all 4 axioms. The first one is here. UV to be Z1. And because that it equals Z1, so it again equals V U. So the first property is satisfied. The second one, suppose that W to be W1, W2, then U and U plus W, V plus W to be that, and if we regroup them together, you get that one is exactly UV and that one is UW. So the second property of definition is satisfied. The third one, if we take C multiplied by UV like that, you get that one, and that equal C U1 V1 and again that is a C U V. So the third property is satisfied. The last one, suppose that you get that one. That by formula it is here, and obviously that number is never negative, and that equals 0 if and only if V1 equals 0 and V2 equals 0, or it means that V is a 0 vector. So all 4 properties, 4 axioms in definition of the inner product is satisfied. That is, the new function we define is an inner product. And here is a remark. A remark saying that any inner product on N square I always has the following form. U and V must be C1 U1 V1 plus C2 times of U2 V2 plus Cn times UN N with all the coefficients C, C1, C2, Cn must be positive. All the number here must be positive. You can see the next one here. I take one function like that, and you see that one is here. We say that we require that any coefficient here is positive, but in the next one I choose that coefficient is negative, and then I show you that one is not an inner product. That is, one of 4 property must be broken, not satisfied. And here you see, let me take V to be that one, and then if we take V and V like that, the function V and V, you get that one. And that is minus 6. Minus 6 is negative. And property number 4 in definition requires that the inner product of V and V must be non-negative, but here it is a negative. That is a property number 4 is broken. And because of that function is not an inner product on S3. In definition of inner product, we require 4 properties, and from those 4 properties, you can easily then you can easily imply the following more property here. If you take zero vector and multiply by v, the inner product, then it equals 0. And you can exchange the plus from the second position to the first position, you get that one. And if you take C multiplied by inner product of U and V, you get that one. So that is the three more property. But you don't have to include that in the division of the inner product. That you can imply from division. Ba tính chất này có thể suy ra được từ 4 tính chất trong định nghĩa, cho nên chúng ta không cần phải đưa nó trong định nghĩa. Trong định nghĩa chỉ cần 4 tính chất kia là đủ. Cái này đều có thể suy ra được. The next, now we follow anything we did for the space I. Bây giờ chúng ta bắt chước tất cả những điều mà chúng ta đã làm cho không gian Euclid Rn. The first one, we can define the norm or the length of any U. The length of U now is the square root of inner product U and U. And property number 4 saying that the inner product of U and U is not negative. So we can put it under the square root. Tích trong của U và U là không âm, cho nên ta có thể có quyền đặt nó ở dưới dấu căn bậc 2. And from here you get square root of the norm equals the inner product of U and U. The next one, that the length of the norm we define already. Now we can define the distance between U and V. Again, the distance between U and V is defined to be the length of U minus V, or by formula it is the square root of inner product of U minus V and U minus V. The next, the angle between two non-zero vectors U and V, that is an angle zeta satisfying that the cosine of zeta equals that one, that number. And that by that number you can once again you can divide it into 5 cases. Opposite direction, the obtuse angle, góc tù, and then the right angle, góc vuông, and then accused angle, góc nhọn, and the last one is the same direction. U and V in the same direction. And we take the middle one, that is the case when U and V are orthogonal, and usually it is denoted like that. And we define that U and V are orthogonal if and only if their inner product equals 0. So anything here we define here is exactly the same as we define for the Euclidean space. Mọi điều chúng ta làm ở đây là hoàn toàn giống với những điều chúng ta đã làm với không gian Euclid Rn. Cái khác duy nhất ở đây là chúng ta làm với bất kỳ một cái tích trong nào. Còn ở không gian Euclid là chúng ta chỉ làm với cái tích vô hướng mà chúng ta đã biết, chúng ta đã định nghĩa rồi. Then some more name. If a vector V has a norm 1, we call it the unit vector. If V is not 0 and the norm is not yet 1, then we can normalize it. It is not unit vector, we can normalize it to get a unit vector in the same direction by divide V by the length of V. Then we get the unit vector in the direction of V. So that is just only some name we follow from the Euclidean space. Now I want to give you some examples. The examples now give you, we are considering something not in n space I. Here, we consider two matrices, two polynomial px and qx like that. They are vector inside the vector space p and x. P and x, that is the space of all polynomial of degree less than or equal n. Then we define the inner product p q to be a0 multiplied by b0 plus a1 multiplied by b1 and so on, and up to an multiplied by bn. So that will be an inner product inside that space. Then you are required the following. Suppose that P to be that one and Q to be that one. In P2 of X, you are required to find the inner product of P and Q. And then, what is the norm of Q? And what is the distance between P and Q? So now is no longer vector geometric vector inside n space. That is now is a polynomial. We can do only on the formula like that. The P, Q, the formula is here. Now we apply A0 to be 1, B0 to be 4, and it is here. And if you apply that formula, you get the inner product of P, Q to be 2. And the second one, the length of Q, it is the square root of Q inner product with Q to be that one. And now it is the square root of 21. Square root of 21. And the last one, first you need to find what is the P minus Q. P like that, Q to be that one. So P minus Q to be that polynomial. Then the distance between P and Q equals the norm of P minus Q. And once again, by calculation, you get that here. That is square root of 22. So for this kind of exercise, what you need to know, you need to find the coordinate of the polynomial P and Q according to the standard basis, and then you can find, and then you can apply the formula here to find the inner product and everything with implies. Once again, some property of norms that is quite similar to the property of the length. The norms is never negative, is non-negative. Second one, the norm equals 0 if and only if the vector u to be 0 vector. And the last one is the norm of c kind of u equals the absolute value of c multiplied by the length of the vector u. And property of the distance similar to that, you have the distance between two vectors u and v is non-negative, and the distance between u and v equals 0 if and only if u and v are the same vector. And the last one, the distance between u and v and the distance between v and u are the same. And for Euclidean space, we have three things. The first one is Cauchy-Schwarz inequality, and here we have it already. And we have a triangle inequality, here we have it also, triangle inequality. And the last one, we have a Pythagorean theorem, Again, here we have the Pythagorean theorems. Why is that? Because in Euclidean space we have a dot product, and here we have an inner product. And from dot product we can imply anything, and from the inner product we can imply the same thing here. So you can see the explanation in the slide I up on the Buddha. So I just only list the inequality here for you to see. That one is again what you know already in high school. That is, the name is orthogonal position in inner product space. In Vietnamese is phép chiếu vô góc, orthogonal position. Now, suppose that U and V be two vectors inside an inner product space V. So please remember that I need the V is inner product space. Inside V we have an inner product. And we suppose that the vector V is not zero. Then the orthogonal projection of U onto V is a vector inside V. Phép chiếu vuông góc của U lên V, thứ nhất nó phải là một vector. I insist it must be a vector. And I believe that you know it already in high school. It is here. V must be non-zero, so we have a straight line containing V, and the vector U to be here, and the orthogonal projection of U on V to be that vector going from the origin to that. So that by geometry we know from high school. But here in this course, whenever we have an inner product, that will be given by the following. The projection of U on V equal k tie of V. The k to be that number U multiplied by V over V multiplied by V. Here. So in the case V is a unit vector. Special case when V is a unit vector, then inner product of V and V equal 1. Then that formula now looks simpler. It is like that because now we don't have that part. We have only projection of U on V equals inner product of UV multiplied by V. So that is a notion of phép chiếu trực giao on a non-zero vector V. Here is examples. Whenever you know the geometry, whenever you know the formula, any exercise is very easy for you. Suppose that you are given the dot product inside R3. You need to find the orthogonal projection of U like that onto V like that. First of all, you know that V is a non-zero vector, so you can do the orthogonal projection of U on V. How to find it? Here. The first one, you need to find UV, the inner product equal 10, and the inner product of V and V equal 5. Then by formula, position of U on V to be Z1, and it is here. If you look at the formula, it is very easy for you to find. And that is a remark, very important for you. I want to insist. Please pay attention to U minus position of U on V is always orthogonal to V. So what does it mean? That I promise you know from high school. If I go back to the previous slide. Here, what I have just said to you before coming back here, I say that vector is the dashed line here is always orthogonal to that one. U minus projection of U on V is always orthogonal to vector V. Cái đường này nối từ vector U tới cái hình chiếu vuông góc của nó, cái đường mà chấm này là luôn luôn vuông góc với vector V. Đấy là một tính chất quan trọng và đấy chính là ý nghĩa của cái chữ gọi là phép chiếu vuông góc. Here I say U minus projection of U on V is orthogonal to V. We are going to use that in define some more things. Now, suppose that U and V are two vectors inside an inner product, and V is non-zero. Then, that one. Okay, that you know already from high school. Very easy. Okay, I forget the formula for some time. You take a look in the picture here. U to be here and V to be that one. And the position of U on V to be that one. And what is the C of V? C of V is any other point on the green line here. Then, what you know? That you know from high school. The length from here to here is always shorter than the length from U to here. Độ dài của đường cao bao giờ cũng ngắn hơn độ dài của đường xiên. Đấy là điều chúng ta đã biết từ phổ thông. The length of that is always less than the length of any skew line like that one. So that is written in the formulas like that one. So I would like to insist that's a geometry. If you look at the geometry, it is very easy for you to remember the formula. That one, the formula here is illustrated in the geometry like that one. Next, autonomous basis and Gram-Schmidt process. The Gram-Schmidt process is I can say it is a nightmare for almost all students. Cái trực giao hóa Gram-Schmidt là một cơn ác mộng cho hầu hết sinh viên học môn này. But before going to the nightmare, we need to have some new notion. Orthogonal. We define two vectors orthogonal to each other already. Now, a system, a set S of vectors inside an inner product space V will be called orthogonal set if any two vectors inside S are orthogonal to each other. Một tập S được gọi là tập trực giao nếu hai vector bất kỳ trong đấy đều vuông góc với nhau. So that is an orthogonal set. Now if here S to be that one, if Vi, Vj equals 0 for any I and j, for any I different from j, then the set will be called orthogonal set. More than that, we have a new notion, we have more notion. Autonomous in Vietnamese is trực chuẩn, because here we have the norm word inside here. Autonomous set a set S will be called orthonormal set if it is orthogonal and all vectors are unique. An orthogonal set in which any vector is unique will be called orthonormal. Then, by formula, you have the following. S to be Z1, we require two things. The first thing, that is Vi Vj equals 0 for any I different from j. That is the same like here. But we require one more thing, that is the inner product of Vi equals 1 for the case I equals j. And if more than that, S is a basis, then we have the notion of orthogonal basis and orthonormal basis. So I summarize in Vietnamese. Một tập hợp S gọi là trực giao nếu hai vector bất kỳ trong đấy là vuông góc với nhau, là trực giao với nhau. Nếu nhiều hơn thế, mỗi vector đều là vector đơn vị thì chúng ta có khái niệm hệ trực chuẩn. Nếu nhiều hơn thế nữa, cái ông S đấy mà là cơ sở thì chúng ta sẽ có khái niệm cơ sở trực giao và cơ sở trực chuẩn. If summarized like that is very easy for you to remember. Here, once again, we're going back to the high school. In high school, you have that one. In R2 or in the coordinate plane, you have I and J to be Z1. They are standard basis, they are standard unit, and now they are standard orthonormal basis because of I and J is a length 1. And similarly for R3, for space, you have I, J, and K to be Z1. With I coordinate like that, J like that, and K like that. And they are standard basis for R3. They are standard unit vector for R3. And now they are orthonormal basis for R3. Đây là ví dụ ở phổ thông chúng ta đã biết với các cái ký hiệu như thế này, ký hiệu quen thuộc như thế này. Chúng nó là cơ sở tiêu chuẩn, chúng nó là các vector đơn vị tiêu chuẩn, và bây giờ trong cả hai trường hợp này chúng đều là các cơ sở trực chuẩn quen thuộc mà chúng ta đã biết in the high school. Here is examples. Suppose that we are given a set S consisting of 3 vectors like that in R3. Then you are required to show that the set is an orthonormal basis just only to find the dot product. The dot product of V1, V2 to be here, V1, Vc to be here, and V2, V3 to be here. So they are orthogonal to each other. So they are orthogonal already. We need only to verify the length only. The length of V1 to be here, V2 to be here. So with that calculation, we can conclude that S is an orthonormal set. Next, in P3, with the usual inner product, we define already like that, and P and Q like here. Then P and Q is defined like that one for any P and Q like that one. Then you are required to verify that the standard basis 1x squared is an orthonormal basis. Basis is already, now we need to verify that those vectors are orthonormal. Then once again, V1 to be that, V2 to be Z1, and Vc to be Z1. With the coordinate 1, 0, 0, 0, 1, 0, and here. And from here, very easy to verify that the inner product of them to be 0, and the inner product of the length of the norm of V1, the norm of V2, and the norm of V3. They all are one soul. And the homework for you, you can verify that. The standard basis is an autonomous basis for P and X, P and C. Once again, I repeat, it is a space of all polynomial of degree less than or equal to n. That one will be very useful criteria for you to verify if a system is linearly independent or not. And after that, we will go into what I call the nightmare of student. But however, I want to reserve the nightmare for the next week. So we stop here today.
Vậy nhiều nhanh lắm mà. Này mẹ là sao?